Okay, so today we're gonna start. We really only have like 3 chapters left, so we're gonna start on one of the last three. This will go on the next test. Chapter 11 and 12 will also go on there. Remember that the 9 and 10 homework is up and due tomorrow. If you haven't done that yet, I will try to get the 11 and 12 homework up sometime today. I'm also, for those of you that asked, there's been multiple people. I'm going to work on getting the grade book a little bit cleaned up today from the makeup test and see how to get those grades all tidied up. And then real quick, I don't have anything pulled up for it, but there's kind of big news that skated through the last couple days. NASA has awarded SpaceX with the contract to land humans on the moon. And so SpaceX has kind of been doing their own thing independently, developing the rocket in South Texas to go to Mars. And they did compete with other companies to get that contract to land people on the moon. A lot of people thought that they were a long shot, and I thought they were a long shot. It just seemed like they took a rocket that they were already developing and repurposed it for the moon. And I didn't think NASA would be very impressed. Well, apparently NASA was very impressed, and the other companies had major flaws in their proposal. And so SpaceX has been picked. And so literally the rocket that they're building in South Texas and will launch later this week is the prototype for the rocket that will land people on the moon within the next 5 years, hopefully. So we'll see how that goes, but that's a pretty big contract for them. I think they're getting close to $3 billion out of that contract once all is said and done. So that's pretty interesting and exciting. So let's see. Coastal hazards. They're going to talk about a lot of stuff. Really, when we talk about coastal hazards, we're talking about flooding and losing of your land. Those are your two big coastal hazards. Obviously, there are other hazards about living on the coast. Hurricanes probably being number one foremost, and tsunamis maybe a close second, depending on where you live. But coastal hazards specifically is like erosion and flooding due to sea level rise or erosion or both. So we're going to go through several things. Their case study for this PowerPoint is Folly Island, which is an island off of South Carolina near Charleston. This island has let's say a murky future. We're not really sure what's going to happen here. And there's another island at the end of this PowerPoint that they kind of compare it to. So let's just go through the bullet points. This is a barrier island. Folly Island is a barrier island off the coast of South Carolina. Barrier to ocean waves that would strike the mainland. It's about 10 kilometers or 6 miles long, less than 1 kilometer wide. So I'm thinking maybe like a shorter version of like Galveston, or what's the other island that's down there? South Padre. Yeah. There's just these long, thin barrier islands that aren't very wide, but can get pretty long. This one's kind of short, but it's still going to serve the same purpose. Most of the island has an elevation of about 5 to 10 feet above sea level. And so you can see the problem here. There's just not any part of the island that's that far above the ocean. And so when big storms roll through, they're going to have a lot of problems. If you get high tides or high sea level rise, you're going to have a problem with that. And so this is an island that's already kind of living on the edge. Typical Atlantic Barrier Island, it is eroding at a high rate. East-facing shoreline has been retreating for at least 160 years. Pair of rocky barriers, jetties, are aiding in the erosion. They're built to prevent the entrance of Charleston Harbor from being blocked by sand, but really they're just making the erosion worse, happen faster. So they are facing some tough decisions on how to adapt and to manage future coastal erosion. With an island so small, you're talking about a very minimal number of people that live there, but if you happen to be one of the people that lives there, it's a pretty troubling scenario you found yourself in. So here is Folly Island down here on the map. You can see that it's relatively long but thin, and it is kind of like the barrier to keep storm waves from hitting this part of the mainland. So, yeah, let's see. They mentioned this jetty here, the South Jetty, and how they put this in to kind of restrict sediment movement in and out of this bay, but that it's actually causing more erosion to happen on the island than before, probably because it's kind of streamlining the flow of water along here, and so maybe you're getting more erosion. Let's see. So, introduction to coastal hazards. They're going to start large and kind of work their way in. So, continental and ocean processes converge to produce landscapes that are capable of rapid change. They're telling us that the coasts are greatly influenced by plate tectonics, and so that means the shape of the coast and also how active your coast is. The United States is a great example. We've got a pretty passive coast on the east side, but a pretty active coast on the west side. And so it's good to kind of think about that, how the East Coast is not really shaped by plate tectonics, and it's kind of been the same for quite a while, where the East Coast has several events that kind of change the way the dynamics work as far as elevation and water flow, rainfall, different things like that. So let's see. We've gone through this. Coast also influenced by climate and organisms. How much rain? How long is your dry season? What kind of organisms live on the beach? Or is there a lot of plants? Is it mostly a bare beach with a lot of animals that dig and burrow? There's a lot of different things that can affect how your shore is kind of fortified. Everybody stop and take a look real quick. I want everybody to focus on this. This was actually one of the most informative things that I got from one of the best field trips that I ever took. So at OU, we took a carbonate field trip to Key West, which is super awesome, like college field trip to Key West. But one of the things that I learned the most about were the mangroves and how mangroves help build land for us, and how there's multiple different types of mangroves that can basically live in different salty conditions. Because the problem with building islands and different vegetation is you have salt water out in the ocean. Most trees don't grow super well in salt water. Most living things on land don't deal with salt water very well. And so when you have like an island ecosystem, let's say this is the island, that's going to come down here, and then down here is like the water, and I'm coming out here. You have salt water for here, for sure. And so there's a very specific type of mangrove that will actually grow out into the waters. It has very deep roots that will come down and form this like big network of intertwined roots as the tree kind of grows up. But these roots can handle salt water very, very well, and they form this like really thick mesh with roots going everywhere. So as my sediment washes off of the island and normally would just go out to sea and be lost to the island itself, the mangroves trap all that sediment in their roots, and eventually it will fill up and the island will kind of extend out to where the mangroves are at. But there's actually 3 different types of mangroves that work really well in this environment. You have the ones that live basically out in the water that are full salt water. Like they love full salt water, that's where they thrive. Then you have like a transition type of mangrove that deals really well with some salt water and some fresh water. Because like in this transition zone, I'm getting fresh water from rain on the island or from water that's actually down in the sediments of the island. And so this mangrove, I forget the names. There's a red, a black, and a white mangrove. And I forget which goes where. I can probably easily look it up. But one of them's in the middle with like some salt, some fresh water. And then there's another one out here that deals with mostly fresh water. And so you can kind of walk from the beach up onto the island and see the different phases of mangrove and see how these mangroves kind of hold your island together and help you build out further. And the rest of the mangroves kind of like reinforce the island as these saltwater ones are pushing further and further out and just collecting more sand and building up your island. And so when you look at places like Key West, which are mostly coral reefs, that's like the base for the island. But without the mangroves, the coral reefs would, because they're long dead now. There are still some live coral reefs, but not a lot. The coral reefs would have long like eroded away, and the islands would be under the sea level. But with the mangroves, they help hold everything in place, and they're really a huge, huge part of island building. So that was one of the like really cool things for me to be able to see on that field trip, was the different trees and how the islands kind of build themselves. And mangroves have floating seeds. So all while you're looking around there, you can just see these like mangrove seeds bobbing along the water. And they're just going to bob along until they find a fresh patch of beach that doesn't really have mangroves in it. And then they're more likely to get planted there and then do their mangrove thing. So island building and keeping your island from washing off into the sea is a huge thing for people who live on islands. Because when you live on an island, that's it. Like, that's the amount of land you have. You're not likely to get a whole lot more. And so it's important to keep what you have. So let's see. Most serious coastal hazards include strong coastal currents. These are going to pull your sand and your land away. Coastal erosion from rain and water that falls on the land, running out into the ocean. Storm surges from hurricanes, which we've already kind of talked about, and tsunamis, which we've already talked about. So each of these are kind of adding to our coastal hazard kind of portfolio, if you will. Let's see. Waves are caused by offshore's wind producing friction over the water. Size of waves depend on how fast my wind is traveling and how far and long it blows. So the longer amount of time it blows and the further distance it blows from and the speed all contribute to create a certain size of wave. They do use this term fetch. Fetch is the distance wind blows over a water surface. That helps build up the size of your wave. So waves become sorted into groups as they move away from their origin. There's a wave called a rogue wave that are exceptions to these groups. They just kind of do their own thing. Obviously, they're rogue. And these can be bad for some boats in very specific, perfect conditions. Let's see. What? We went from 11 point. Oh, I went the wrong way. My bad. I was like, why is the PowerPoint wrong? But I was wrong. Let's see. Waves continued. Rogue waves appear to form by constructive interference. And basically what they mean by constructive interference. Do y'all know what they mean by constructive interference? Y'all taking physics? Gotten into waves and waveforms and interference patterns and stuff. Basically, if I have a rogue wave line up at the same point as a regular wave, they're going to combine to equal a supergiant wave. That's basically the way waves work. If they were opposite, like if the peak of my rogue wave lined up with the trough of my other wave, they would kind of cancel each other out and be a smaller wave. But rogue waves can be extremely dangerous. They say beachgoer. They can also be a little bit more dangerous to boats as well. So they just kind of come out of nowhere. You don't see them coming. They appear for just an instant and then are gone. It's the rogue wave. So here's a picture of a rogue wave off the side of a ship, and that's got to be kind of terrifying if you're a deckhand on a ship. Here they talk about waveforms. I guess I didn't need to write that on the board, but they talk about waveforms, wave height, wavelength, wave period, and how you can kind of, well, I guess they don't go over it, constructively interfere or destructively interfere. Let's see, feel the bottom. We've kind of talked about this. They do give you the half depth wavelength. This is why waves rise towards the shore. They feel the bottom of the ocean. You can kind of see it here. Out in the sea, you have waves of a certain depth, and basically, depending on the size of your wave, you have a particular depth in the ocean where you will feel that wave too. And if you're deeper than that level, you're just not going to feel any waves. Like let's say you're a fish You'd see the waves going over you, but you wouldn't really have any motion. If you're, say, like in this area, for every wave that goes over you, you just kind of do this little circle thing. As you're sitting still, you're just kind of oscillate with the waves. And the point is, if you're inside that level, as your wave comes up towards the ocean, as soon as the bottom of the sea reaches up into that wave movement level, my wave is going to start to rise out of the ocean because it's starting to interfere with the bottom, which is going to push it higher up onto the shore. And so that is, you can actually measure that. It's going to happen at about half of the wavelength deep. So if my wavelength is 10 feet apart, if I have 10 feet in between one wave and the next wave, 5 feet down, half of that wavelength is the depth at which I will start to feel the waves, or the waves will start to feel the bottom of the ocean. So it's about half the wavelength, which is nice. Let's see. Wave sets generated by storms are called swells. Swells enter shallow water, become unstable, and break. The break is where your wave curls over. That's what the surfers are always looking for, is nice wave breaks. Mathematical equations can be used to predict wave height, period, and velocity. And I guess that relates back to surfers again. If you're a surfer, you check the wave reports and you know what the waves are going to be like before you even head out to the beach. Waves move in open ocean with little energy lost. Energy is spent reaching the coastline. Wave energy is proportional to the square of the wave height. So the higher the wave is, the more energy it has. And they just don't lose very much energy traveling through the ocean. It's a pretty efficient process. On the coast, wavelength and velocity decreases, wave height increases, the wave period is consistent. So what they're telling you here, your waves get shorter, they come more close together and faster, and the height is going to increase. And so everything just gets compacted and kind of pushed upwards as the waves come ashore. Let's see. Variations along the coastline. Your coastline's weird. It's really weird. You have all sorts of little inlets, and it's not a straight line. It's very much many squiggly lines. So they're saying irregularities in the topography cause variations in wave height as it approaches the shore. A single wave is called a wave front. Let's see, effects of wave refraction. You have wave normal, which is perpendicular to wave fronts, pointing towards the shoreline, and then wave refraction causes normal to converge and diverge. And I think, yes, they have an example of this. So basically the point is, the wave's coming in nice and flat. You can see it here. It's just a straight wave coming right on in. And we would think that it would just come in nice and straight. And so it would hit this rock straight on, and it would hit this beach kind of at an angle because it's coming in straight the way that it was. In reality, we get this refraction. So this rock, this peak rock out here, is going to kind of drag the middle of the wave and slow it down in a way. So as the wave comes, when it hits the middle's going to slow down, and the ends are going to kind of bend around and come inward. And what this results in most of the time, unless you're on like a really flat beach and it's a windy day, the waves want to hit the shore perpendicularly. That's what their goal is always to do in physics, not like a mental goal. They're not alive, but they always want to hit the shore perpendicularly if possible. And so that's what refraction is going to try to do, is kind of steer them in the proper way. Is this even the right pen? I don't know. Let's see. Breaking waves, plunging breakers, spilling breakers. Just remember, when they're talking about a breaking wave, that's the waves that curl over the top that you're looking for if you're surfing. So they have plunging breakers and spilling breakers. Your plunging breakers pick up quickly, typically on steep beaches, and they're more erosive, so they're going to kind of like smash down, probably similar to the ones we see the surfers hitting with the nice like pipes that curl all the way over. And then spilling breakers, these are waves that spill gently, typically on wide, flat beaches, more likely to deposit sand. These are the ones that just kind of gently roll over themselves as they come into shore. Probably the ones that you would like to swim in. Yeah. So these are your plunging breakers. your big curling rip pipes that the surfers want to surf in. And then these are your spilling breakers. These are what you want if you've got a beach chair on the beach and are trying to spin all day there. You don't want to be fighting the waves. Nice recreational beach. Nice surfing beach, I guess. So let's see, beach form and processes. Okay, real quick. The beach consists of loose material. That it doesn't matter what beach you're talking about or what the material is. They're all loose. Nothing's really compacted at the beach unless you're on like a cliff beach. So the beach consists of loose material which is accumulated by wave action on the shoreline. The type of beach material depends on the source of the sand. So white beaches generally aren't sand unless the sand has been like brought in or trucked in from somewhere else. Most of the time when you get white beaches, it's a lot of shell and coral because what lives right on the beach in the ocean is a bunch of like ocean-going animals that have shells, and a lot of times you have corals right near the beach. So usually your white sand beaches are broken up tiny pieces of that and not actually like quartz sand that we're thinking from deserts. Especially if you're anywhere near a hotel, they probably trucked in sand from somewhere else. Black beaches like Hawaii are going to be a lot of volcanic rock. Brown beaches have a lot of quartz and feldspar. So those nice, like really bright colored white sand beaches are usually not your natural stone. Let's see. The beach onshore, landward extent of a beach onshore or lakeshore. You can have dunes that line your beach. You can have a line of permanent vegetation. You can have a sea cliff or bluff. There's all sorts of different ways that your beach kind of transitions into your mainland. Beaches are divided into two sections, berms and beach faces. The berm is the beach portion that slopes landward, formed by deposition of sediment by waves. And then your beach face is the beach portion that slopes towards the water. And what they mean, not all beaches have a berm, but basically what they mean is I have my ocean out here, right? And I have my beach that's coming up here. So if my beach comes up this way, this is the beach face. Is that what they call it? Yeah, beach face. So there's got to be stickers or like T-shirts for people that live on the beach that just says like resting beach face, right? I mean, you write the word beach face and you're like, okay, I see where this is going. But anyways, as the storms or the waves come, they can, instead of just kind of having a flat beach here, they can pile up sand on this beach, especially if you get really big waves during high tide. They can kind of pile up sand and then you can have it come back down. And so if you have to walk up a hill to get to the other side, which is the beach, this is what they're referring to as the berm. So the berm slopes away from the water. The beach face slopes towards the water. Not all beaches have berms, but probably a lot of natural ones do. This is not the pen. This is not the pen you're looking for. Let's see. The beach offshore. So offshore of the beach, we have three different zones. We have the swash zone, the surf zone, and the breaker zone. And remember that offshore means out in the water, away from the shore into the water area. So swash zone, surf zone, breaker zone. And these three are basically the swash zone is like your transition from the water to the land. This is where your waves wash back and forth. So literally, if you're standing in an area where the wave comes in and goes back out, and it's like half wet sometimes, half dry sometimes, that's the swash zone. Then you get to the surf zone, where your turbulent waves move after the waves break. And then you get to the breaker zone, where the waves become unstable, peak, and break. This is usually a little bit further offshore, depending on your shore profile. So here's their example. Like I said, the swash zone is going to be your transition from wet to dry, where your waves are washing back and forth. You can really see the sand just pushed back and forth, back and forth. Then you have your surf zone. Your surf is where your waves have already broken, and you're getting interaction between your waves coming in and out a little bit, but mostly just your waves coming in. Your out water is probably staying down towards the bottom. And then your breaker zone is where the waves get pushed up, they become unstable, and they get that nice break. If you're on a nice recreational beach, you want to get your boogie board out in the breaker zone to catch some sick rips. Let's see, sand transport. So how do beaches move sand? This is where we really get into coastal hazards, coastal erosion. Where is my beach going? I bought all this beach. I paid a bunch of money for my beach house, and now my beach is gone. This is important work here. So sand transport, we have littoral transport, which is sand moved parallel to the shore. This is also called beach drift or longshore drift. It's just your ocean water naturally moving down the shore. And has everybody been to like the ocean beach? At least once, yeah. And you've experienced like where you leave your parents and you go out into the water and you play for like 30 minutes or an hour and you come back and you panic because you're like nothing looks the same. Your parents are gone, the towel is gone, all the families look different, and you're like, where am I? The longshore current and the beach drift just push you down the beach, and you have to walk like 5 minutes that way to get back to your parents. Does everybody remember that? At least a little bit? Yeah. The current pushes you down the beach. And so that's what you experienced was the longshore drift. And it's not just you the current's pushing, it's also pushing sand down there, moving sediments around, and causing havoc for the people that live around there. Let's see. Longshore currents, current that flows parallel to the shoreline as a result of the up and back movement water in the swash zone. The updrift and the downdrift indicate the direction in which the sediment is moving or accumulating along the shore. And yes, we get a nice picture here. So you can see the waves are coming in a little bit at an angle. As your refraction happens, you can see this wave is kind of curling in. Your waves are coming in and out and just slowly moving your sand down the beach. If you're out here playing in the water, you get moved a little bit faster and you end up down here. You got to walk back to your beach towel in a little while. Let's see, the level of sea is constantly changing. So now we're on to sea level change. We have two different types of sea level, and this is important for y'all to remember. We have relative sea level. This is going to be the sea level at my particular place and location. So the position of the sea at the shore. This can be influenced by movement of both the land and the water. And so relative sea level is going to refer to things like tides, the sea level in your particular bay. It can depend on a lot of things, where the position of the moon is, which direction the wind's blowing, how much deposition you have in the land. And so relative sea level can rise and fall all the time. And just because yours rose doesn't mean that everybody's rose. It's just your particular sea level. Where eustatic sea level, which is a weird word. I don't know that I've encountered the word eustatic too many times outside of this. But eustatic sea level is your global sea level. This is everyone's sea level taken as an average. It's controlled by processes that affect overall volume of water in the ocean and the shape of the basins. So what affects eustatic sea level is literally how much water do we have tied up in ice at the poles or in the ice caps, and what are the continents doing? What are plate tectonics doing at the time? Is that keeping the continents sitting a little bit higher on the crust, or are they sitting a little bit lower on the crust? That can actually affect a lot of stuff too. And that's something not a lot of people really talk about with global sea level change. Some of the biggest changes we have seen over time have been more associated with plate tectonics than freezing water or actual air surface temperatures. That being said, we can't control plate tectonics at all in the slightest, and we can control how much we pollute and affect the atmosphere and the environment. And so that's really the only thing we can focus on. Let's see. Eustatic sea level change rises or falls when the amount of water in the world's ocean increases or decreases. Climate or average air temperature is important because temperature increases can cause the volume of water to expand. So they're not even just keying on like melting water, adding more liquid water to the oceans, but literally just a degree more in temperature is going to cause expansion of the oceans, and that's a lot of water. It may not seem like very much, but it could be a lot in certain areas. Temperature decreases, and that's going to cause contraction of the water. Changes in temperature cause ice on land to melt or snowfall to increase, which we're pretty familiar with. Ice sheets, glaciers melting, stuff like that. And then, like I said, tectonic processes also. If your plates start to move around and your ocean basin gets squeezed or stretched, that's going to affect how much water it can hold and what your sea level looks like. So they talk about relative sea level a little bit. It can change with weather conditions, tides, how much soil you're depositing or not depositing, and little things like glacier melts or earthquakes can cause the land to rise, can introduce more water. There's all sorts of things that can happen. Let's see, geographic at risk, regions at risk for coastal hazards. Coastal hazards, the good news for us here in north central Texas, coastal hazards pretty much just happen on the coast. We don't have to worry about it here. Unless you're a lake owner that, like we saw the other day, you built your lake house on a cliff, then we got coastal hazard issues. But in general, we're not dealing with a lot of coastal hazard issues around here. But yeah, if you're near a body of water, you're on this list. The Atlantic, the Pacific, the Gulf, the Arctic coast in North America, large lakes such as the Great Lakes, the Great Bear Lake. Someone Google Great Bear Lake. I gotta know where it's at right now. Never heard of Great Bear Lake. I'm guessing Canada because the next lake listed is Lake Winnipeg. So,
Yeah, it's like in Canada.
but where in Canada? What province? Not that I know all my Canadian provinces, but
It just says in the forest of Canada.
just the forest
It
of
says
Canada.
cities.
We're
It's
so
the largest-
disrespectful to Canada.
It's the largest lake entirely in Canada.
Oh, nice. So they're not like splitting it with the United States. But they're just like, it's in Canada. It's in that Canadian forest.
It's the Northwest Territories.
Northwest
It
Territories.
is
All right.
intersected by the Arctic Circle.
Oh, so it's like way up there. All right, yeah. To be fair, that's the part of Canada where you don't even really like different. It's just, it's up north. Yeah. No one lives there.
It's kind of
Oh, I bet it's awesome. I bet it's like super pristine and like you walk around there. Probably hasn't been very many people there over the last decade. Let's see. Coastal erosion. Coastal erosion is a more universal hazard. All 30 U.S. states bordering the ocean have it. Canadian provinces bordering the ocean have it. Those bordering the Great Lakes. So any large body of water, you're definitely going to have some risk. Strong nearshore currents are also common problems on coastlines that have regular strong surf conditions. California and Hawaii, any coastal breaking waves, rip currents in the U.S. Gulf and eastern coast. We don't experience these too much, but the rip currents are pretty bad. If you live near the beach and you do a lot of swimming, rip currents can be extremely dangerous and troublesome. So let's see. Coastlines that are subsiding are at particular risk. Yeah. Let's keep going. Tectonically passive. What are they showing me here? I guess basically yes. It's not oriented the right way, but this is roughly in the most generalized way the difference between the East Coast and the West Coast. The East Coast is tectonically passive. There's no plate interactions going on the East Coast. It's all just the North American plate. And so they have these gentle slopes and sandy beaches. On the other side of the continent, more West Coast, California, it is tectonically active. And so not to say that California doesn't have beaches, but on a large scale, if you look at the coastline of California, they have very steep hills and cliffs right on the edge of the ocean there. Again, not to say that they don't have many beaches, they do, but in general, their coastline is going to be a little bit more vertical coming right out of the water compared to the East Coast, which is going to be very gently sloping. And so that means they're going to have very different risks for coastline hazards. Particularly, you can see because of this undercut wave, California is going to have a higher risk for landslides and different collapses of that sort. Let's see, effects on coastal processes, create a hazard for both individuals and communities. Obviously, the individual hazard is safety during swimming and property safety if you live near the ocean. For communities, you have long-term hazards related to erosion and sea level rise. They talk about barrier islands and spits, probably as a way that we construct things to try to slow down this erosion. Can move an entire island. The inlets between islands or the separation of a spit from the mainland. Poor places for coastal development. Let's see if they have a picture for that. I don't really know what they're getting at here when they're talking about barrier islands and spits. I mean, obviously they're problematic because they're out in the ocean. I don't know if they're like arguing for the movement of an entire island, or are they saying that the effects of coastal processes can move an entire island, inlets between islands, or the separation of spit from the mainland? I think that's what they're saying. I think they're saying this is an effect of the coastal processes, and they're showing you here with Hog Island, which is off the coast of Virginia near Chesapeake Bay. And these different colored lines show you the erosion that's happened. So you can see way back in 1852 to 1871, this island was much bigger, especially down in the southern portion of the island. It came way far out and had a huge island imprint. It looks like it even had like a little bay right here. And as erosion continued to happen, the island has just gotten smaller and smaller and smaller until you see it in its present day configuration. And they're probably a little bit worried about this island as far as how much longer it's going to last and whether the ocean's eventually going to take it. It's almost time to go.
Yes.
Nice. We'll go ahead and end here with rip currents. Let's see, did I get halfway through, or was I dilly-dallying? And show 31, I dilly-dallied a little bit. We'll see. But we'll pick up here tomorrow. Rip currents, wonderful.